Welcome back. So far, we've built a solid foundation using standard linear regression to predict outcomes. But now we're going to tackle a new challenge. What happens when the real world refuses to move in a straight line? Standard linear regression operates on one very strict assumption. It assumes the relationship between your input variable and your target output is always perfectly straight. This animated diagram shows data points forming an upward bending curve. Forcing a standard linear model here fails. A rigid line shoots straight through, creating massive error gaps. By using polynomial regression, the model bends into a smooth curve tracking the data, shrinking those errors to nothing. Real-world phenomena rarely follow perfectly straight paths. To accurately predict complex trajectories, our mathematical models require the flexibility to curve along with them. So how exactly do we force a mathematical engine built entirely for straight lines to suddenly draw a curve? Our foundational equation starts with the familiar linear baseline, y equals b0 plus b1x. The trick to polynomial regression is expanding the sequence. We add new terms by squaring the original input for x squared, cubing it for x cubed, or raising it to higher powers. We are taking a single original input feature and artificially generating a set of brand new features directly from it. Inside your dataset, that original x column is mathematically multiplied against itself to create entirely new adjacent columns for your squared and cubed data. By treating these upgraded powers as distinct inputs, the system executes multiple linear regression on a single variable to achieve a curved output. There's an inherent paradox here. The resulting visual shape is entirely curved, yet the underlying mathematical structure running the calculations remains strictly linear. To understand why, we separate the model's features from its parameters. The features are the data inputs, our x, x squared, and x cubed, which stretch the shape. The parameters are the coefficients, the underlying weights that determine how much influence each feature has. This split screen illustrates the crucial rule of this model. Polynomial regression is nonlinear in its features on the left, but perfectly linear in its parameters on the right. Because those parameters never contain exponents themselves, standard optimization engines like gradient descent still function the same way without breaking. This duality is a mathematical hack. It offers the visual adaptability of a curve paired seamlessly with the computational stability of linear regression. The exact flexibility of this curve isn't random. It is tightly controlled by the user, who must define the polynomial degree, often represented by the letter n. This is a graph featuring an interactive degree slider. As we increase the degree from 1 up to 5, the mathematics add more turns, dips, and inflection points to our model's predictive curve. If we choose a degree that is too low, we risk underfitting. The model remains too rigid to capture the true underlying pattern. This side-by-side comparison shows the opposite extreme on the right, overfitting. When the degree is too high, the model becomes wildly chaotic. It hyperfixates on random noise in the data, hitting every single dot but failing completely to map the actual trend. The ultimate goal of the data scientist is to find the structural sweet spot in the center pane, the exact polynomial degree that captures reality without memorizing the noise. Finding this balance is essential when predicting complex trajectories, like forecasting shifting stock market cycles or tracking the rapid spikes of viral population growth. By transforming our original features into higher powers, linear regression can conquer curved relationships. In our next video, we'll open up Python and implement this exact model in scikit-learn.